Thank you very much. It's good to visit Institute for the first time. It's a very nice arrangement and everything. As Dipendra said, I'll talk about Siegel modular forms. So these are generalizations of elliptic modular forms, and I'm very happy that Ulf went before me and he's already got you ready with the elliptic story. What I want to do, as I say it on the title, classical and adelic aspects. So basically, the way I like to work with Siegel modular forms is look at them as classical modular forms. There's a lot of number theory that you're interested in, and oftentimes you can solve these problems in a very general setting if you move from classical to adelic. And going back and forth and getting answers for one from the other side is a very fruitful endeavor, and it's very useful for the younger people at least to learn these things. Oftentimes you are good at classical stuff or the adelic stuff and are scared to go to the other side. So I want to tell you that you don't need to be so scared with that, and I'll lead you in the discussion for Siegel modular forms. And so there are 4 talks. The first 2 are classical aspect, the second 2 are the adelic aspect. And what I want to do, for example, today is just set up the basic concepts of classical Siegel modular forms. And tomorrow we can see exciting applications, which are just out of results from the last 5 to 10 years. So I want to show you basics, push you to the edge of what is going on, and try to show you interconnections between different techniques. That's the main goal. I gave a Gyan workshop a year and a half ago in ISER Pune, and Dipendra was the one saying that, why don't you give a condensed version of that over here? So there are quite a few familiar faces who were in that Gyan workshop. So I will not feel offended if you doze off. It's a repeat, but you might hear something new and interesting that you missed out the first time round. I took the notes from the Gyan workshop, and it's now being published as a lecture notes in math, Springer lecture notes in math, so it will come out in June. So that's a good reference for you guys, and I have a PDF if you want, I can share it with you. So that's a good reference to do this. So I want to start with some motivation, and I saw Ulf's talk, and his first slide, almost his first slide was quadratic forms, and I said, I'm going to start exactly from what he's saying. And so, okay, slightly different, but the same idea. So what a question that you can ask is, you have a quadratic form. So here we have a quadratic form Qx, and this comes from matrix A, which is even, symmetric, and positive definite. And even means all its diagonal entries are even numbers. Symmetric and positive definite, you know. And you get a quadratic form in m variables here. And then basically you ask this question. This is the same similar thing that we saw in the previous talk. Rq of n is how many ways can you represent an integer by this quadratic form. And well, so the problem is maybe I find an exact formula, or at least give asymptotics as n goes to infinity. So some kind of idea of this one. And one of the ways of attacking these quadratic form and representation numbers, just like in the previous talk, is to write down this theta series, where you just sum over all elements in Zn, and you put the Qx in the top, and you get this nice formula in terms of e to the 2 pi I and z, and the coefficients are exactly your representation numbers. And the z is from the complex upper half plane. So just like Ulf was saying, this, he did this in the specific case of sum of 4 squares. You can do this in general, and then the idea is that this thing that you defined artificially on the space of complex numbers or the upper half plane has these infinite symmetries. It's actually a modular form. So it's a modular form of weight m by 2 and level n, and n is somehow something to do with the matrix A that you started with. So NA inverse is also an even integral matrix. So you get modular forms with a level as well as the weight is half of the dimension of what you had. And then if you have information about these modular forms, then you could essentially write down maybe explicit formulas or at least asymptotics. So for example, in the case where you had the quadratic form is sum of 4 squares, then this theta series ends up being a modular form of weight 2 and level 4. And we know in that space, it's a vector space of dimension 2. You can write down the explicit formulas of the generators. And if you then write down this theta in terms of those generators, you get an explicit formula for the RNs, the ones that Ulf was writing down on his slides. In particular, you can show that Lagrange's theorem, which says that every integer can be written as a sum of 4 squares. You get it automatically out of something like this. So this is a good idea, and this is a good motivation for modular forms. And what we want to do is we want to look at a much more general setting where we are not just looking at how do quadratic forms represent integers, but the more general problem is if I fix matrix T now, if it's an n by n matrix, I want to count the number of ways this matrix T is obtained by the quadratic form given by the fixed A that we have. Now already in the previous case I was looking at all integers. Here I'm not going to get all symmetric matrices. So for example, all n by n matrices, there are some conditions I need. So what are the conditions that I have? For even to expect R cube to be bigger than 0, I need of course this thing to be symmetric. I need it to be positive semi-definite. And 2 times t should be even. So t should be half integral. So already you see that when you're generalizing it, you're not going to represent every single matrix. There is a subset which is naturally coming up as well. And so if you set up now this much more generalized theta series, the n is coming from the n by n matrix, it indeed turns out to be what's called a Siegel modular form of weight m by 2 and level n. So what I want to do is this is just working as a motivation to see that these generalized representation problems and their corresponding theta series are going to connect us to these objects called Siegel modular forms. And so it's a good point to pause and see what these Siegel modular forms are. So let us start with basic definitions. So what I want to do is I want to use this to speed up my life, to put up here things that I don't want to spend too much time talking, and then I want to use the board to slow down a little bit and show some details. So let us see how this combination works. Hopefully it will be fine. So what I want to start with, well, I want to start with a positive integer. R is a commutative ring. And I want to first define my symplectic group. So GSP2nR. This is the subgroup of GL2n, which preserves a symplectic form. So G transpose JG is mu of T times J, where my J is the matrix given by this guy, and mu of G is in GL1. So when I say GSP2n, I'm saying that it's a size 2n by 2n matrix. It's not the rank that I'm talking about. And here the mu, which goes from GSP2nR to GL1R, is called the multiplier. So this is a homomorphism in this case. And if you look at its kernel, so if you look at so SP2nR is defined to be all G in G SP2nR with multiplier 1. So this is the symplectic group that we are going to deal with. And I just want to write down some very easy to write matrices which belong to this guy. And you can already see that if I have n equals 1, GSP2 is exactly my GL2. There is no condition coming out of this. So this is indeed a generalization of your elliptic case. I'll try to point out these special things as we go along so that you're convinced indeed that the Siegel modular forms are higher dimensional analogs of elliptic modular forms, so that even though you see something new, you should remember the familiar things about modular forms and not feel too scared with big matrices or something. Okay, so some examples. You could have matrices of the form x1n, and if such a matrix has to belong to the symplectic group, you need it to be symmetric. So this is the analog of 1x01 inside your GL2, and you have G transpose inverse. These are zeros, where G is in GLN. This is another subset or subgroup of the symplectic group. Once again, if your n is actually 1, this is just your torus that you have here. You of course have J which belongs to this belongs to your symplectic group as well. And one more example I want to write down. This is Kn is how I denote it. X, Y, Yx or minus Yx. So when I write down blocks like this means I am breaking down the 2n by 2n matrix into n by n blocks. And here so X and Y are n by n matrices, and so that it belongs to the symplectic group, there is some relation between X and Y. So I have X, Y transpose is Y, X transpose, and X, X transpose plus Y, Y transpose is identity. And if your R is real numbers and n is equal to 1, this is exactly cosine theta, sine theta, minus sine theta, cosine theta. So this is your SO2 that you have written down. So this is the higher dimensional analog of that. And you can see already that these matrices already are in here. It's very easy to check that the similitude is 1. This thing also has similitude 1. So we are just looking actually at examples, all of them coming from sp2n. And you will notice if you look at the defining condition, the determinant of any matrix here is, well, the determinant square is mu g to the power 2n. So if you are inside sp2nr, 2nr, then determinant of g squared is actually equal to 1, because your similitude is 1. Well, the question is, can you have a minus 1 or are you forced to have a plus 1? So is it inside SL2nr, or could it have a minus 1 determinant? So a fact of life is that sp2nr is actually always inside SL2nr. And for a general ring R, it's kind of complicated to show. You show it by induction and so on. But if you restrict it to R being the real numbers, then you can actually show that the symplectic group sp2 and R, where R are real numbers, is generated by matrices of these 4 kinds. In which case, if you look at the first 3 guys, the determinant is already 1. And all you need to know is what happens to matrices of this kind, and you can do a very clever trick to show that the determinant is always positive. Well, if it is positive, it has to be plus 1, because we have a plus or minus 1 as a choice. So it's a very nice exercise to check that this is actually determinant 1 matrices. So this is your symplectic group, and this symplectic group acts, yes? The group is generated by 1, 2, 3 and the compact. Yes, yes. Okay, I am sorry. You are absolutely right. What I meant was, yes. It is indeed generated by 1, 2, and yes, you're absolutely right. What I wanted to say was when you are looking at the real numbers, you can use the Iwasawa decomposition to see that every matrix is a element in the product of these guys and the compact here. So no, it's not generated by these three. If you look at sp2 and z, then it's generated by these guys, but sp2 and r, no, you see, you won't. Right, right. You're absolutely right. Yeah, so that's a much easier proof. You're absolutely right. If you use the Bruhard decomposition, why am I getting confused? Okay, okay. Yeah, you're right. Bruha. Right, right, right. Right, absolutely right, absolutely right. Perfect, perfect. Okay, so this symplectic group now acts on the Siegel upper half space, and the Siegel upper half space is also very much similar to the complex upper half space, and it's defined by the following. So this is our Siegel upper, yes. Right, right. I am not sure. Okay, so Siegel upper half space of genus N, this is now matrices, N by N matrices which are complex matrices. You want them to be symmetric and you want the imaginary part to be positive definite. And so this is exactly your complex upper half plane is all complex matrices with imaginary x plus iy where y is positive, but now these are all matrices here. And so if you want to take GSP2 and R and you want to act on this, so basically you want to take G equals A, B, C, D, and you want this to be an element of GSP2N, and now I am leaving the general ring and looking at real numbers. I want to look at those which have similitude positive, and this one I want to act on Z in Hn by the formula Gz is Az plus B Cz plus D inverse. So this is analogous to your A tau plus B divided by C tau plus D, but of course now we have matrices, which basically means we have to work a little harder to make sure that this makes sense. So for example, what you have to show that if you denote J of Gz to be Cz plus D, the first thing you have to show that this is invertible. Because if this matrix is not invertible, you can't even write this. So you have to first check that it is invertible. And this is pretty not very complicated. Some basic linear algebra using the fact that things are positive, definite, and so on. And after you show it's invertible, you can actually show a nice co-cycle relation here. So if you have G1, G2 acting on Z, then you have J G1 acting on G2Z times J of G2Z. So as soon as you can define G of Z, you can actually prove a co-cycle condition. This is very straightforward right from the definition of G of Z. So this tells me that I can define Gz, but that still does not mean that my matrix which I started in Hn lands in Hn. I need to see that it is symmetric and its imaginary part is positive definite. So as I said, there is some amount of work to be done, a little more than in the genus 1 case. And so for example, you can show that the imaginary part of GZ is given by mu of G C Z bar plus D transpose, imaginary part of Z times C Z plus D. Inverse here and inverse here. And even though this looks complicated, you should see that this is, in the genus 1 case, imaginary part of GZ is Y divided by absolute value CZ plus D squared. So this is what you get when you look at everything in genus 1. And in the higher genus, you have to work with matrices, and something like this gives you that this is indeed positive definite. And you also, using the defining property of being a symplectic matrix, you can actually show that what you get here is also symmetric. So this is some exercise using the defining properties of being a symplectic matrix. And once you get this, then you are having an action of GSP2nR plus on Hn, and the fundamental domain, etc., which Ulf was saying in the previous talk, it's the whole theory is there, worked out and everything, but it's just much more tedious to write down in this case. And I'm not going to do that, but I just wanted to tell you that the Minkowski domains and fundamental domains and everything are all figured out in details. One thing I can write down is the measure on Hn that you have, which is invariant under this action. So that will be used in defining Petersson inner products and so on. So invariant measure on Hn is given by d star z is determinant of y to the minus n minus 1 times dz, where this guy is just dx dy. And I'm writing z as x plus iy. And this is the usual measure on the complex upper half plane that you do, which preserves action of SL2R, is indeed dx dy over y squared. So this is now the analog of that. And yes, N is the genus, and yes, there is, and if I start talking about it, I'll go into an area which I don't know much about, so I will not in that case. So basically, what we did was just the basic setup of the group and the action of the group on the Siegel upper half space. There is one cute fact that you can get out of this. For example, you have this Siegel upper half space. If you have the complex upper half space, you know that every element in the complex upper half space is non-zero, right? By definition, because the imaginary part. How do you know that every matrix in Hn is invertible? Its determinant is non-zero. So Z in Hn implies determinant of Z is not equal to 0. So I'm telling this because even though you work with this for 10, 20 years, sometimes these kinds of things stump you. So me and my collaborator Ralph Schmidt, we were working on something and we needed to do this, and it took us an hour to look at determinants and we couldn't make head or tail. But then we realized that if you take your G to be equal to minus identity, this one, then your Z is exactly J, G, Z. And this theorem says it's invertible. So there is a general thing which tells you invertibility of these things, and we were stupid enough not to realize this soon enough, and it took us at least an hour to realize that you should not try to show determinant is non-zero by first principles and everything. Maybe it's true that way, but this is a nice way to see. Yes, so that further reflects how dense we were, and we could not even realize this basic thing. Indeed, so in this case, you can see it in the other way, namely, you can realize it as this thing right here. When you act as by the matrix, it works out. Perfect. So once you have this action, you can now define your Siegel modular form, and in this case, here?
Yeah.
What goes wrong when M is or all kinds of bad stuff. Okay. I cannot really tell you very easily right now, because if you want to go to half integral weight Siegel modular form, there is a theory and everything. But I'm kind of writing down the simplified version, so it's easier to write that down. Later, actually, I'll write down a theorem where M is divisible by 8, because I'll say that's the nicest story there. So, but if M is odd, then it's much more complicated. Okay, so for me, gamma n is sp2 and z, so I'm not modding out the the -1. And now it's very similar to what we had in the elliptic modular forms case. You have a function on the Siegel upper half space. There is a positive integer k, and Siegel modular form of weight k with respect to gamma n is a holomorphic function. It satisfies this automorphic condition with respect to the action of gamma n on the upper half plane. And when n is equal to 1, you want it to be bounded function as you go in the imaginary direction. And this thing forms a vector space, and we denote it by mk of gamma n. And so you can see this is the generalization of the elliptic modular forms we have been seeing in the previous lecture. And what I want to do is I wrote down these, we erased these matrices already, and I'm not going to need this one either. So the different kinds of matrices we wrote down as the symplectic matrices tells you special properties that this F satisfies. So for example, F of z plus x is F of z for all symmetric integer matrices now, because we want to be in gamma n. You also have F of, what is this one? You also have F of g, z, g transpose is F of z for all g in gl and z. I'm basically taking the automorphic condition and applying it to these matrices that I wrote down. And so you get these, oh, I miss the, no, this is perfectly what we have. And then I have one other condition. If I apply the matrix negative identity in gamma n, it tells me that mk gamma n is just a 0 if kn is odd. So when genus n was 1, k odd gave me just the trivial modular forms. And I also have the thing corresponding to S. F of minus z inverse is f of z times determinant z to the k. So very quickly we get these symmetries like we were looking at earlier, and this thing here tells me that I'm going to get a Fourier expansion. And the Fourier expansion in this case looks like where this thing is over T is symmetric, positive semi-definite, and half integral. So symmetric and half integral because the characters on this space are exactly given by e to the 2 pi I trace Tx, where T is a symmetric half integral matrix. I have the T, instead of Tx, I have a Tz because I'm looking at holomorphic. So holomorphic tells me in the y variable I get an exponential as well. The only thing I don't get is this greater than or equal to 0. And to achieve that, for the n equals 1 case, I have this boundedness condition which gives me that my Fourier coefficients depend on positive semi-definite matrices. For the higher genus, there's no condition, but it turns out it's automatic. For higher genus, there's something called as Kocher principle, which tells me that I have a condition like this. Automatically, I don't need to assume it, which gives me a Fourier expansion of this kind. So Fourier expansion is much more complicated now. It is indexed by these matrices. And for example, something like this, if you apply it to this Fourier expansion and do a suitable change of variable, you get A of G transpose Tg is A of T for all T and G. So G is up here and T is down here. So these Fourier coefficients have a natural invariance. Yes?
What does it mean by, sorry, what is F holomorphic in this case exactly?
Holomorphic is, so this thing has a holomorphic structure, and so there is this version of Cauchy-Riemann equations if you want in these variables, and so holomorphic is, well, you take your genus 1 case and you just generalize that, yeah. Okay, so these are modular forms, and now because the Fourier expansion is complicated like this, there is no easy way to define Cusp form. In the elliptic modular form case, we said A of 0 is 0 is a Cusp form, but in this case, there are too many things which are not positive definite, and so the intuition for Cusp forms comes from the following simple observation. So if you have genus 1, then Cusp F is Cusp form by definition if and only if A0 is 0. But A0 you can achieve as the limit as t goes to infinity of f of it. So if you just restrict to the imaginary part and go along the imaginary axis to infinity, you look at all the exponentials, all of them become 0 and you just left with A of 0. And this is the reason why one of the motivations of defining what's called the Siegel phi operator. So what does it do? You take f in mk gamma n, and then you define phi f. So this is here, and a z prime is in hn minus 1. So out of a function which is on hn, you construct a function on hn minus 1, and the way it is defined is limit t goes to infinity of f z prime it if it exists. And you can see in the elliptic modular forms there is no z prime, and you get this constant, which is your a0. And what about this limit exists? Well, you can substitute for f its Fourier expansion. You can check that you're allowed to change the summation with the limit, and then individually all of them do have limits. So this limit does exist, and what the Siegel operator does is indeed gives a map from mk gamma n to mk gamma n minus 1. So you get a function on hn minus 1. You can see the holomorphy is not a problem. For the automorphic condition, you have to take gamma n minus 1 and somehow very cleverly embed it in gamma n. And then using the automorphy of f, you can show the automorphy of this thing as well. And then this guy has a very nice Fourier expansion. summation T1 equals T1 transpose, where T1 is now in a smaller size, and the coefficient comes from T1 0 0 0 and e to the 2 pi I trace T1 z prime. So the Siegel phi operator picks up all the Fourier coefficients of f which are not positive definite. So you can show that if you have a matrix like this, and if you don't have positive definiteness, you can arrange it to be in this form. So basically it's collecting all of these guys, and then the Siegel Cusp forms are precisely kernel of phi. Just like in the elliptic case, the elliptic Cusp forms are the kernel of the map f goes to limit t goes to infinity f of I t. And if you want to know in terms of Fourier coefficients, well, something is a Cusp form if and only if all these Fourier coefficients are 0. Namely, the Fourier coefficients live only on the positive definite guys. So that's the analog in this case. Strictly semi-definite. Yeah, that's exactly right. Absolutely right. So all of these vanish, and the ones that survive are t bigger than 0 terms. Absolutely right. And now these guys, of course, if these guys vanish, then these Cusp forms have better convergence, which allows you to define your Petersson norm. So this is denoted by Sk gamma n, and suppose I have a f in here and a g in mk gamma n, I can now define the Petersson norm, which is the integral over hn mod gamma n f of z g of z bar. But this is not invariant under gamma n, so you need to do determinant of y to the k, and then you have your d star z. And you've seen Petersson norm for elliptic modular forms case, it's exactly this guy. And to make sense of everything, you need to know what this fundamental domain, etc. is, and I'm just telling you it can be found out, and I'm not going to tell you the details about it. But we have now a Petersson norm on the space of modular forms, where at least one of them is a Cusp form. We need the cuspidality for the convergence of this integral here. Okay, so we have set up the basic definition. We see that they are a little more complicated than our usual elliptic modular forms case. But if you are okay with seeing these bigger matrices, they are really genuinely generalizations of your elliptic modular forms. And so if you're seeing it for the first time, I'm telling you, don't be scared of it. It's not too bad. If you've already seen this, of course, this puts up everything out here so that we can now look at some examples. So the first example is what we looked at earlier. You look at this quadratic form Q of G coming from a matrix A, which is even, symmetric, and positive definite. And this one can be put into a theta series where the coefficients end up being these representation numbers of the quadratic form. And then it turns out, so the most simplified situation is where I make an assumption that M is even and the determinant of A is equal to 1. So unimodular, even, symmetric, positive definite matrices. In that case, I do get a Siegel modular form of weight half of M with respect to gamma n. And I'm assuming unimodular because if I have unimodular, then this n for level, which we saw in the very beginning, is actually equal to 1. So you don't get any level in this case. And if you are wondering if these guys ever exist, well, they do. If 8 divides M, then you can always find these unimodular lattices. And so this gives you a class of examples. Of course, this is not a Cusp form, because if you take t equals 0, then RQ of 0 is not 0 already. So clearly not Cusp forms. It will take us quite some time to come up with any example of a Cusp form for the Siegel modular case. But this is our first example. The second one is actually what usually comes first, but this time it's the second one. It is the Eisenstein series. So let us do it here. So this is example number 1. Second one is Eisenstein series. And here the definition is E, K, genus N, Z is defined as determinant of CZ plus D to the minus K, and A, B, C, D is in gamma N modulo gamma 0 N. And what is gamma 0 N? It's a subgroup of gamma N where the C is equal to 0. So it's in the Siegel parabolic, if you know about Siegel parabolics. So this is the subgroup here. And you can see that this is exactly the analog of 1 over mz plus n to the k. And you sum over all m and n in a lattice. And so this thing, it turns out, if k is even and k is bigger than n plus 1, then this converges. And it is non-zero mk gamma n. So indeed, if n is equal to 1 and k is even, then the first time we see it is k equals 4. So like in the elliptic modular forms case. So these are sort of the very basic examples of Eisenstein series, analogs of the Eisenstein series that we saw for the elliptic modular forms case. And the next example I want to give is the first deviation from elliptic modular forms case, because you don't see them in the elliptic modular form situation. Because if I want to construct an Eisenstein series of genus n, maybe I can take an integer r which is smaller than n, and a Cusp form of genus r, a smaller genus, and then use that to construct an Eisenstein series. So if you're familiar with the way Eisenstein series are constructed out of induced representation, then you're looking at some parabolic and looking at a Cusp form on the levy of the parabolic, and then you are doing the standard construction. So in this case also, you can do it in the following classical setting. So this is Klingen Eisenstein series. I'll tell you why it's called Klingen. So you start with any r between 0 and n. You take a Cusp form of genus R, and your any matrix Z in Hn, you can look at the top R by R block. This is an element in HR. So you take this element in HR and you call it Z star. So everything in Hn has a component in HR. And then you use a very similar construction like this, but you weight the determinant by the Cusp form. So the way you define it, the Eisenstein series is genus n, weight k, and comes from a Cusp form f of genus R. And what you did was you did determinant Cz plus d to the minus k, but then you weighted it by f of the star of Gz. And you sum it over all gamma n, but now you quotient out something extra, which is, or something different, which is the set on which this product is invariant. And what is this PR? Basically, there is a prime, B prime, C prime, D prime, which is actually in your smaller group gamma R, and the U's are from GL n minus R. So this is what's called the Klingen parabolic, where you have a smaller symplectic sitting on this side, and then there is the rest of it is a GLN. So this is a Klingen parabolic. And you will see that if my R is equal to 0, then the U takes up the whole space and the lower block becomes 0, which is exactly my gamma 0 n. So when R is equal to 0, my P0 is exactly gamma n 0, and then this thing is just boiling down to my Eisenstein series right here. So these are called as Klingen-Eisenstein series, and it turns out, so this is something I can tell you, it turns out that they are indeed modular forms. So theorem says that for n bigger than or equal to 1, R between 0 and n, K for convergence we need some condition on the weight, and K even. So and F is in S K of gamma R. In this case, my Eisenstein series E n R K of F is actually a modular form of weight K in gamma n. And a very interesting feature is, well, I'm constructing this out of a Cusp form. So if I take my Siegel phi operator and apply it n minus R times, I end up getting my Cusp form back. So when I apply it n minus R times, I end up getting a modular form of genus R. What do I get? The one I started with. So the Klingen-Eisenstein series increases the genus from a Cusp form of genus R to a modular form of genus N, and the Siegel operator brings you back. So this Klingen-Eisenstein series is a very important example, because in a certain sense, Cusp forms and Klingen-Eisenstein series is all you have. And what I mean by that is the following. So M K gamma n is S K gamma n and E K gamma n, and this thing is the span of E n R K F, where you are running over all R and all F in S K gamma R. So all you have is Cusp forms and Klingen-Eisenstein series. And if you think of it for a little bit, then you might feel a little surprised, because if you know the construction of Eisenstein series from induced representations on parabolics, these groups have other parabolics, not just the Klingen one. You could have a Siegel parabolic. Its levy is whatever the levy is, you can put a Cusp form on that, induce and get an Eisenstein series. The point is, it will never be holomorphic unless you started by one-dimensional representation of the levy. So only the degenerate Siegel-Eisenstein series end up being holomorphic, in which case they are just obtained very similar to these guys. Otherwise, if you're looking at what you might call Siegel-Eisenstein series, they never fall into this space. So only Klingen-Eisenstein series and Cusp forms are enough to generate this thing. Say it again. What if you, instead of a Cusp form, you just put some other modular form? You can do that, yes. You can do that, certainly. So the construction here could work if F is not a Cusp form, but then a theorem like this would tell you that at some point you started with a Cusp form. If at genus R it was not a Cusp form, maybe it's actually coming from a Cusp form from a lower genus. So essentially, you are constructing things out of Cusp forms of smaller genus. But the construction, you are right, is valid. Here there is no cuspidality important here. The modularity is what is required to write down this definition. So far we have not seen any Cusp forms, and I want to show you one way to get a Cusp form. And unfortunately, no delta function here. So, a Cusp form. And I want to look at n equals 2. So if you have two different Cusp forms of two different genus, and you construct Eisenstein series of genus n, they, well, the Klingen-Eisenstein series are not related to either of them, because, for example, if you have starting from R1 or R2, this tells me that after applying it n minus R1 plus 1 times you get 0. In the other case, n minus R2 plus 1 times you get 0. So it's these Eisenstein series are different for sure. Actual relation between them, I don't know. Maybe there is a relation, but I don't know what kind of relation we are looking at. Okay, so Cusp form, basically what I want to do is I want to use this Siegel operator to construct a Cusp form. So I want to define chi10 to be equal to, I'm taking E10 2 minus E4 2 and E6 2. So you can see that the weight is 10, and I'm looking at the difference of these two. So this is a modular form of weight 10. I want to normalize these, so I'm putting a tilde up here so that I'm normalizing these so that the 0th coefficient is 1, which basically is a useful thing to do. And now if I applied phi operator to it, then the phi operator goes through and I actually get E10 tilde minus E4 tilde and E6 tilde. So the Siegel operator takes the Eisenstein series of genus n to the Eisenstein series of genus n minus 1. And the point is that if you're looking at weight 10 genus 1, the dimension is 1. Modular forms of weight 10 with respect to SL2Z, the dimension is 1. And so these two guys are a multiple of each other. And because I normalized it, this is actually equal to 0. So what I got is that chi10 is a modular form of weight 10 which is in the kernel of the phi operator, so it's a Cusp form. So this gives me a Cusp form. Of course, one crucial thing that you have to show is that it's not 0, because 0 is trivially in the cuspidal space, and that requires some amount of effort. If you take your Z, this is genus 2, and you write this as tau Z tau prime, you do a Taylor series in the Z variable and show that the Taylor series coefficients are non-zero. So it's a much more complicated thing to do, but it's a very clever trick to focus on something slightly different, and it gives you non-zero. So this is not equal to 0, and it's an element in S10 gamma 2. Same idea, you can define a chi12 and a chi35. So you can define chi12 and chi35. And the reason I'm telling you about these two is because if you look at, so this is a theorem of Igusa from 67, which says that if you look at the ring, so this is all genus 2. Then this is actually a ring which is generated by E4, E6, chi10, chi12, chi35. But this is not free. There is a relation which is chi35 is some kind of a polynomial expression in the other 4 variables. So this is the structure theorem for the graded ring. And so Igusa writes down the polynomial in full details. It's one full page of his paper. The coefficients are numbers which are 15, 16 digits long. And this is 1967. So how did he get those? So Ralph was telling me that he was talking to Ibukiyama. And Ibukiyama said that a few years ago he sat down and tried to find out this polynomial by using computers. And to the very last coefficient, it was exactly Igusa's polynomial. So completely verified that this horrible thing that Igusa has. I mean, whenever you get papers to referee like this, you kind of take some liberties in not checking every single coefficient of a polynomial which is one page long, right? So usually you're supposed to trust the referees, and usually you're supposed to do a good job of refereeing yourself. But a double check, independent double check is always good. So this thing is checked by Ibukiyama, apparently. So this is, of course, a story told by someone to someone, and now me to you guys. So there might be some loss of truth in the middle, but hopefully not. Yes. Or f to be 0, so that is, no, f is just a constant then. It's not 0, it's the constants. So constants. Yeah, we can talk about that later. So what I want to do is, once you have the structure theorem, I want to look at one more example, which is perhaps I can get to this example later. So I was going to talk about Saito Kurokawa lifts, but maybe a good time to introduce Saito Kurokawa lifts might be in the beginning of tomorrow's lecture. So I want to briefly instead show you what's happening in the world of modular forms where you don't have just full level gamma n. So you could define Siegel modular forms with level as well. And most of the lectures I'm not going to talk about general level, just keep things simple, but to just tell you what goes on, and that the fact that it's much more complicated in the Siegel modular forms level than the elliptic modular forms is a good thing to know. So what we have is, well, you can define a principal congruence subgroup of level n. This is exactly like in the genus 1 case. These are all matrices in sp2 and z, which are congruent to 1 mod n. And then a congruence subgroup is any subgroup of sp2 and q, which contains one of these principal guys with finite index. And for example, if you're looking at genus 2, then there is these 4 guys which are standard ones. So the first one is called a Borel congruence subgroup. So for example, here if I switch the first 2 rows and first 2 columns, the n's all come down here. And so the Borel congruence subgroup is upper triangular mod n. So those are the Borel congruence subgroup. The Siegel congruence subgroup is modulo n, I get a 0 here. The Klingen one we have kind of seen, it looks a little more complicated. So this is the third here. These are 2 maximal parabolics which give you the Klingen congruence subgroup. And then there is a very interesting one which is the paramodular subgroup, where you have the exact this guy, but you put an extra n inverse. So here this does not have integer entries, it's really in sp4q. And you can define Siegel modular forms with respect to any one of these congruence subgroup, and then you have to specify which congruence subgroup and what is the level. So you have to specify the integer n and what kind of congruence subgroup you have. And I just want to give you one example. So this Klingen-Eisenstein series we wrote down, we could actually generalize it to level. And you could start with elliptic Cusp forms with respect to gamma 0 n. And gamma 0 n is your familiar thing. And you can write down 2 possible ways of writing the Eisenstein series by weighting with the Cusp form. So one of them depends on the Klingen parabolic, the other one on the paramodular one. And these 2 guys gives you 2 different Klingen-Eisenstein series. One of them is a Siegel with respect to the Siegel congruence subgroup. One of them is with respect to the Klingen congruence subgroup. So this is, so Ralph Schmidt is my colleague and Alok Shukla is his student. So in his PhD thesis, he did a adelic version of the Klingen-Eisenstein series, and in that process, he came up with the first concrete classical examples of Klingen-Eisenstein series written as a classical function. So this is kind of brand new. And this is a good example of modular forms with levels. Okay. As I said, we will not talk about modular forms with level at all beyond this point. Next week, I'm going to give a talk which is going to be about non-trivial level, but when it happens, I'll tell you what they are. So right now, we can kind of keep this as a thing in the back of our mind that they exist, but we don't need to worry about it. Okay, so once we have modular forms, definition, and examples, next thing we want to do, like we do in elliptic modular forms, is Hecke theory. We want to write down Hecke operators and try to see if we can get a basis of Hecke eigenforms, and that is going to let us define L functions. So the goal for today is to write down L functions corresponding to Siegel modular forms. I'm going to give you two L functions, and let us see what's happening with the Hecke theory here. So there is some generalities which I'm going to go through pretty fast because this is something common to every single Hecke theory for modular forms. So you take Gn to be integer matrices in the symplectic group with positive similitude. And then your Hecke algebra is just a formal algebra which is made up of linear combinations of these double cosets. And you can define a multiplication of these, which depends on the single coset decomposition. So there is a way to come up with these coefficients depending on some kind of combinatrix of these coefficients here. And this is something you do for any kind of modular forms. This is the first thing you write down in general for elliptic modular forms as well. I assume Ulf is going to do it tomorrow, and we'll see if he does, yeah. And what we want to do is for any prime p, I can restrict, instead of Gn, I can look at only those whose similitude is a power of p. So those are called Gnp. And using those, I can get a sub-algebra. And I can write that as Hnp. And this is the local Hecke algebra at a prime p. And the first very important thing is that your Hecke algebra can be written as a product of the local Hecke algebras. So you have a very nice decomposition. Now, in the genus 2 case, we know that the Hecke algebra at a prime p has two generators. Here we have n plus 1 generators, which is exactly the correct number. So you're fixing the prime p, and I have things with similitude p and things with similitude p squared. There are n plus 1 algebraically independent generators. Okay, and just like in the elliptic modular forms case, you can define Hecke operators parameterized by positive integers m, where you collect all the double cosets with the same similitude m. For example, if m was equal to p, then you just have this one thing. If, sorry, shaking too much, okay. If m is equal to p squared, then you take all of these guys and you also take additionally identity matrix and p squared times identity matrix. So you can write down what these tm's are. And these Hecke algebras act very naturally on modular forms, and the action is given by the following very nice formula. So action of Hn on mk gamma n. So if I take a modular form here and I take a g in Gn, I can define Tg as the double coset corresponding to this G. And the first thing you do is do a disjoint decomposition into single cosets. And the way Tg acts on F is by sum over I slash kgi. So those single coset representatives. And F slash kg applied to Z is essentially F evaluated at G applied to Z. You take the determinant Cz plus D to the minus K. And you also have a factor corresponding to the similitude nk minus n times n minus 1 over 2. So for example, if my G was in gamma n, then this would be just equal to f of z itself, because this would give me f of z, so it would be an invariant thing. And so this gives me way the Hecke operators can act on Siegel modular forms, and then it's a very standard thing to show that what you get is a function on the Siegel upper half plane, but it is not any random function. If you started with a modular form, you end up with a modular form. And the idea being that if you apply a gamma here, the gamma gets applied to the right or the left, one right here, but you can move it to the left by changing the representatives of the single coset decomposition. And so you get lots of nice properties of the Hecke algebra, namely Hn acts from mk gamma n to mk gamma n. It preserves Cusp forms. So the Siegel phi operator commutes with the action of the Hecke algebra. It's also self-adjoint. So if F is a Cusp form and G is some modular form, then TGFG is this thing right here. And it's a commutative family. So commutative Hn, commutative algebra. So basically what this allows us to do is it allows us to take the space mk gamma n and simultaneously diagonalize it with respect to all these Hecke operators, and you get a Hecke eigenbasis. So you have a basis of simultaneous eigenfunctions of Hn for mk gamma n and also for sk gamma n. And in this case, you can actually get an orthogonal basis. And so basically, the Hecke operators allow us to have this very nice basis of Hecke eigenforms. And once you have a Hecke eigenform and you have the Hecke eigenvalues, that allows me to define what are called is the Sataki parameters. So you see, my Hecke algebra at prime P is generated by n plus 1 algebraically independent operators. So it turns out, so I'm going to write down this classical Satake P parameters. So my F is a modular form, which is a Hecke eigenform. Eigenvalue is lambda g for each one of these Hecke operators. It turns out there are P complex numbers alpha 0 to alpha n with the property that if I take any g in my similitude P to the R, the Hecke eigenvalue lambda g is completely determined by these complex numbers and some exponents dij. And what are these Dij's? That is the only contribution that G makes. So when you take the double coset, write it as single cosets. You can always do it so that the D is upper triangular with powers of P in the diagonal. So those exponents are which come here. And so this is a pretty complicated looking formula. Why should every single Hecke operator be written in terms of these n+1 complex numbers? And a better answer. So there's a classical proof of this due to Andrianov, etc., which is way complicated. A much easier way is to see it via representation theory and the Satake map, and maybe we'll look at it later. But this gives me these nice n+1 numbers called as Satake P parameters for every prime P. And this is exactly what allows me to define my L function. So my F is something like that. So I'm going to define LSF spin. This is product over all prime numbers LPSF spin, where each one of these factors is the reciprocal of 1 minus alpha 0 p to the minus s, product delta equals 1 to n, 1 I1 I delta less than or equal to n, and you take alpha 0 and then alpha I1 up to alpha I delta of p to the minus s. So for example, if I had genus n equals 2, then I have an alpha 0 factor, I have an alpha 0 alpha 1, alpha 0 alpha 2, and an alpha 0 alpha 1 alpha 2. And in general, this is a degree 2 to the n. So there are 2 to the n factors here. So it's a pretty complicated L function. And of course, I'm giving it as an infinite product, so it converges in some right half plane. And this is called as the spin L function for your Siegel modular form. Yes, this is only the finite places. I'm not putting the gamma factors in yet. So one of the things that is very different now as opposed to the elliptic modular forms case is that in the elliptic modular forms case, when you define the L function, you don't need Hecke eigenforms. You just take a Dirichlet series and write it as an L function. And so you could ask, is there a connection between a Dirichlet series and this L function here? And there is. So if you look at the Tm's and the eigenvalues lambda m, and you make the Dirichlet series made up of the eigenvalues, then you can show that it actually factors into product of primes, where you have a Dirichlet series with only lambda p to the r's. And this p part of the Dirichlet series indeed evaluates my spin L function up to some polynomial. And this polynomial capital P is something quite complicated. It's a degree 2 to the n minus 2 polynomial. So for example, if my n is equal to 1, this is degree 0, and the Dirichlet series actually computes the L factor, which is exactly what we know from our elliptic modular form story. If genus n is equal to 2, then 2 to the n minus 2 is equal to 2, and so you have a complicating factor. But in this case, you can actually write down what it is, and it's a very nice, simple one. And you get this very nice formula in the genus 2 case, which says summation m bigger than or equal to 1 lambda of m over m to the s is zeta of 2s minus 2k plus 4 inverse spin. So because there is a 2s here, that's the degree 2 polynomial that you see. So it's a much simpler one. If your genus n is bigger than 2, then this is something nasty, and you can't write it as a nice Euler factor like a zeta factor or something. And that is one of the difficulties for proving theorems about spin L functions or using the spin L function and the Dirichlet series. So of course, in the genus 1 case, you don't write the Dirichlet series necessarily in terms of Hecke eigenvalues. You write in terms of the Fourier coefficients, right? an over n to the s. And in that case, there is no difference between summation an over n to the s and lambda m to the s because it's just up to a constant. In the case of Siegel modular forms, the relationship between the Fourier coefficients and the Hecke eigenvalues is much more complicated. So you have a formula of this kind. Yes, if you have a Cusp form and you take a Mellin transform, then you indeed get a Dirichlet series, which is sum over all coefficients t, a of t divided by determinant t to the s. And it's a valid Dirichlet series, but it is not an Euler product. So it's not an L function. So that's the difficulty here. That thing is too big, basically. But that's a good point. You can do that, but it doesn't give you the natural L function theory that you would like. So the other relation that you have in this case is the following. So if you take a coefficient t0 and it's something called as a fundamental Fourier coefficient, namely determinant of 2t0 is a fundamental discriminant of a quadratic extension, and suppose that quadratic extension has class number 1, so I'm telling too many conditions here, but the upshot is that the Dirichlet series corresponding to Hecke eigenvalues gives you a relationship between Fourier coefficients only in the ray corresponding to a t0. So this is completely unknown. Even though you know all Hecke eigenvalues, you don't know all Fourier coefficients. Because if you know a t0, then you know its ray. But all of these, there are infinitely many. So it's quite a mysterious relation. And a very natural thing to ask here is, can I have two Siegel modular forms with the same Hecke eigenvalues, but which are having different Fourier coefficients? Multiplicity 1. Can you have two Siegel modular forms, say Siegel cuspidal modular forms, which have the same L function, but they are different? And at least in the full level case and the genus 2 case, for the longest time, it was an open conjecture. People thought the answer should be yes. When you look at level and you don't, when you look at non-trivial level, then Schulze-Pilow came up with some counter examples. But this is brand new theorem by Ralph. And this is only possible. So what does the theorem say? It says that if you leave out finitely many primes, and for all other primes, you look at all of these Hecke eigenvalues for all powers. If they match up for two modular forms, then their weight has to be the same and they are multiples of each other. So this multiplicity 1 is highly non-trivial, and this is only possible because of the recent work of Arthur, in which he is. So what Ralph did is he took Arthur's book. He said, okay, what is happening for SO5? SO5 is PGSP4, which gives representations corresponding to Siegel modular forms. And then he divided them into 6 categories. And he said that if your Hecke eigenform is with respect to full level, I only get 2 of those categories. And then he knows enough local representation theory to say it's multiplicity 1. So this is just a very new thing. And also if you have paramodular new forms, it works out as well. So it's a very, it was an open question for the longest time. And it's only with super heavy machinery that we know that it is true. There is no direct proof. And you can already see it's extremely complicated. So there is no reason a priori to expect that this thing is true, but it is. This is only for genus 2, absolutely right. Higher genus, we have no idea. Okay, so maybe 5 minutes to mention some of the nice properties that we have for the spin L function. And the nice properties we have is, well, to begin with, it's only convergent in some right half plane, but In fact, we have a meromorphic continuation and a functional equation. So we are still at n equals 2. And if I define a completed L function as 2 pi to the minus 2s, so this has meromorphic continuation to C, and it satisfies a nice functional equation so this is again genus 2. The location of poles, this thing has at most 2 simple poles at k and k minus 2. So the location of poles is also very well known. And so in the genus 2 case, we really know a lot about these spin L functions. The relationship here with the Dirichlet series is very nice and under control. We have a nice multiplicity 1 theorem in genus 2. We have nice analytic properties in genus 2. And the reason I am emphasizing genus 2 is we know a little about genus 3 and nothing about genus higher than 3. So for n equals 3, the meromorphic continuation was proven by Ralph Schmidt and Mahdi Asghari some time ago. And very recently, Pollock showed functional equation and finiteness of poles. So he got a new integral representation for this L function and was able to get this. And beyond n equals 3, we really don't know its analytic properties. Spin L functions are in general way more complicated because, well, they are not the natural map of the L group. So this is a spin map is much more complicated. And so you will see that the spin L function has a lot of mysteries. The standard L function has fewer of those. And so what I'm going to do, last thing is I'm going to write down the definition of the easier standard L function, and we will finish right there. So now general N, again my F is in mk gamma n, Hecke eigenform, and it has a Sataki p parameters. So the standard L function is again defined as an Euler product. And each one of the factors in terms of the Sataki parameters is given by 1 minus p to the minus s, I equals 1 to the n, 1 minus alpha I, and 1 minus alpha I inverse. So this is my standard L function, and the analytic properties for the standard L function for general genus is known due to Bucherer since 1985. So that's already known. And what I want to do, I know I'm a minute over. So what I want to do is tomorrow I want to start with the spin L function and the standard L function and use very simple analytic properties of both of these guys to give you very interesting applications which we can derive quite easily. The theorems are deeper, but if you reduce it to the simplest case of full level, we can actually come up with very nice theorems just coming out of these properties of these L functions. So we will start with these L functions tomorrow and discuss some applications of their analytic properties. And time for lunch. Yeah. Thanks. Yeah. Let's stop.